Okay guys, so on today's agenda, we're going to start talking about triangles. We're going to talk about why triangles have 180 degrees in them. We're going to discuss constructing perpendicular bisectors, concurrent lines, and points of concurrency, also known as the circumcenter. They don't usually refer to it as as points of concurrency, but you never know, so it's good to know that they're also called that. But mostly they're called the circumcenter. We're also going to talk about what can a perpendicular bisector tell us about a triangle, what can an angle bisector tell us about a triangle, and we're also going to talk about the incenter of a triangle and a point of tangency, which is something that we've discussed in the past before, and we can actually expand on that some more now. So let's talk about exactly why triangles have 180 degrees. Well, here we have a quadrilateral, which has four right angles of 90 degrees each. And if you take 90 degrees and you multiply it by 4, you get 360 degrees. So every quadrilateral has 360 degrees. Well, you've probably heard before, maybe from me, that if you take away half of the quadrilateral, well, now what you have is a triangle. And if you take those 360 degrees and divide them by 2, what you end up having is 180 degrees. So that's one reason why a triangle has 180 degrees. But there's another reason why a triangle has 180 degrees. If you look here, I have a straight line, and I measured the degrees of that line with my protractor. I went from 0 all the way to 180, and we can see that a straight line has 180 degrees. Well, here I also have a triangle, and in my triangle I have 78 degrees, 39 degrees, and 63 degrees. And if I add all those three up together, you can be sure that they add up to 180 degrees. Well, you might be asking, what does a triangle have to do with a straight line? Well, if I take my triangle and I cut off the edges, we'll see in a second. Let me cut off that angle. Let me cut off that angle. And let me cut off this angle as well. If I take the three angles that I cut off and I bring them up to the line, you'll notice that my three angles together form a straight line. That's why a triangle has 180 degrees, because the three angle tips together create a straight line when all their edges are put together. Now, let's talk about constructing perpendicular bisectors, because we're going to have to do that on our own in a minute. Right here I have a right triangle. With this is 90 degrees, this angle here is 34 degrees, this angle here is 56 degrees. And of course, if I add them all up, they're going to equal to 180 degrees. Well, the base of this side of the triangle is 6 inches, and the base of this side of the triangle is 4 inches. So I'm going to construct a perpendicular bisector. Well, if you remember, in order to construct a perpendicular bisector, in order to bisect something, all I really have to do is cut it in half. Well, here I have a ruler that's 6 inches long. Here's 3. Here is A. Here's B. Here's segment AB. And if I want to indicate that AB is being bisected, of course you know that I have to put congruency marks. Those congruency marks indicate that segment AB has been bisected. Well, let me take my triangle here and let me bisect the base. I'm going to grab this end right here, this corner, and I'm going to bring it over to this corner here. I'm going to fold it over, making sure that the corners touch, that the bottoms are straight, that they match together, and then I am going to put a crease in it like so. And so my 6-inch base has been bisected. Now, if you're not 100% sure that this is in the middle, well, let me do this. Let me put it here. Let me grab my little ruler here, and let me match it up. Again, this is 1 to 6 inches. Here's 3. There's my line, dead smack in the middle. So I've bisected my base. But better yet, not only have I bisected it, I've also created a perpendicular line to the base. So let me put a red mark there to indicate, yeah, that is perpendicular there. So this is a perpendicular bisector. This segment right here, this line here, is bisecting my base, and it's perpendicular with my base. Well, I can also make a perpendicular bisector with this base here. It's 4 inches long. I'm going to grab it. I'm going to bring one corner over to the other, like so. I'm going to make sure that the sides are straight, and I'm going to crease it up, making a perpendicular line. And when I open it up, I can see that my base is bisected. This should be the middle point, and this line is perpendicular. Well, if you don't believe me, let's take a look here again. Here's my ruler. Here's 1 inch. Here's 4 inches. And there is 2 inches right in the middle of my line. So we can see that this is a perpendicular bisector. Let me draw a red line here like this. Let me put a little right angle there. They're perpendicular. Now, you might be asking yourself, well, Mr. C, can I make a perpendicular bisector with this side here? Sure you can. Just bring them over, fold them over, make another crease, and what we have now is another perpendicular bisector. Here, and it's right there. Now, you might be noticing something. You might be saying to yourself, Mr. C, wait a minute. I notice that these 3 lines are all converging on one point. They're all converging on one point. And if you made that observation, that's a good observation to make. That's why these 3 lines are known as concurrent lines. They're concurrent lines because they're all coming together to this one point here. And this one point, where they all come together, right here, is known as your circumcenter. That's your circumcenter. So, or my point of concurrency. Okay, so these are concurrent lines, and this right here is my circumcenter, or my point of concurrency. Well, let's see what happens with other triangles. I want you to notice that in a right triangle, the circumcenter is on the edge of the triangle. Let's see what happens with other kinds of triangles. Well, here I have an acute triangle. I know it's acute because if I measured all the angles, they would all be less than 90 degrees. And it's actually easier to make perpendicular bisectors with patty paper. So, which is what we're going to be doing later on. So I'm going to make a perpendicular bisector of this base right here. I'm going to take my paper. I'm going to trace it over. I'm going to make sure that the corners meet. I'm going to make sure that the lines are straight. And I'm going to make sure that I make a perpendicular crease. And there I have one perpendicular bisector. It is bisecting my base, and it is perpendicular. Let me just fill that in with red right here. And I'm going to make a right angle so I know I've done that base. Now, I'm going to take this base as well. And I'm also going to create a perpendicular bisector here. Let me bring that over. Make sure the lines are matching, the corners match, and it's a straight line. Let me make a crease. And there I have another perpendicular bisector to the base of my triangle. It's perpendicular there. And finally, I have one last base here, and I'm also going to make a perpendicular bisector there as well. And it is so much easier to see when you have patty paper versus regular paper. So I'm going to crease my paper there, and notice that I have another perpendicular bisector. And what do you notice about them? What do you notice about all the perpendicular bisectors? Well, if you notice that they intersect here, you're correct. All my concurrent lines are intersecting at one point, and that one point, ladies and gentlemen, is called my what? My circumcenter. So what would you give as a definition of a circumcenter? What would you name that in your own words? We'll talk about that later. But I want to point out another difference. Notice before that my point of concurrency was on the edge of the right triangle. This one, notice where is it? It's inside where? It's inside the triangle. It's inside the triangle. So before my point of concurrency on the right triangle was on the edge. In an acute triangle, it's where? It's in the center. Well, here I have an obtuse triangle. And let's see if we can make some points of concurrence, some lines of concurrency, and see where the circumcenter ends up. So I'm going to put these together here. Going to make sure the corners touch, make a straight line. Going to make it perpendicular. Okay, so there's my perpendicular bisector. There it is. Then I'm also going to take this base here. I'm going to make sure that my lines are straight. Make sure the corners touch and that the lines match. I'm going to go like that there. So I have another perpendicular bisector right here. And then I'm going to get this last side here. I'm going to bring in, touch my two corners, make sure they touch, make sure the line is straight. Make a perpendicular line. Make my perpendicular bisector here. And you might be saying, Mr. C, but wait a minute. None of the lines, none of the concurrency lines, none of the concurrent lines are intersecting. Where's the point of concurrency? Where is the circumcenter? Well, if you look a little closer, you're going to notice that all of the lines don't actually intersect in the circle. If you keep going, my circumcenter happens to be where? Happens to be outside of my triangle. So for an obtuse triangle, the circumcenter is going to be on the outside. All the perpendicular bisectors come together on the outside. For an acute triangle, all of the perpendicular bisectors come together on the inside. And on a right triangle, all of the circumcenters come in together what? On the edge. So we can see a difference between different kinds of triangles and how that relates to their circumcenter. Okay? Next, let's talk about what we can find out about perpendicular lines, or what perpendicular bisectors can tell us about a triangle. Well, here I have another right triangle. Again, it's this base here is 6 inches. This is 34 degrees. This is 90. This is 56. And this is a typo here. This should be 4 inches. 4 inches. And I made sure I went and I measured the angles before I drew these lines here. Well, let's pretend for a second that I want to bisect each one of these angles. Let's see here if I bisect each one of these angles. Well, if I bisect them, let's see what happens here. I'm going to take my 34 degrees and I'm going to bisect it. I'm going to bisect it like so. So I'm bisecting that angle. I'm cutting it into 2 equal angles. I'm going to take my 90-degree angle and I'm also going to bisect it. I'm going to put my little line right here. Do that. And I'm going to take my last angle here and I'm going to bisect this angle as well. This 90 cut into 45 and 45. And you're going to notice something interesting here. You're going to notice that all of my angle bisectors come together at one point. Now, is this point here called a circumcenter? Is it called a circumcenter? The answer is no, because a circumcenter is made from the perpendicular bisectors. These lines here are not perpendicular bisectors. These lines here are angle bisectors. angle bisectors. So by the way, this point right here is called my incenter. It's called my incenter. The point where all my angle bisectors touch is called the incenter. And the incenter is the same distance from all of the sides of the triangle. The incenter is equidistant from all of the sides of the triangle. Well, if the incenter is equidistant, excuse me, it's not equidistant from the sides. I'm sorry. The angle bisectors. I'm sorry. Are yeah. You know what? They are equidistant from the sides, and I'm going to prove it to you right now. Let me grab my protractor here, and I'm going to put my protractor at the center of my circle. There's the center. Okay. I'm going to measure this from one end to the other with the pencil being on the edge of the circle. And I'm going to try to superimpose a circle here from the edge. And look what happens. Oh, make sure I keep it on the edge there. Look what happens Look what happens there. My angle bisectors are this point here, this incenter, is the same distance from this edge of the triangle to this side of the triangle to this side of the triangle. Well then, wouldn't that make this a radius? Because a radius is the same distance from the edge of the circle. So the angle bisectors give me a point that is the same distance from all of the sides of the triangle. Oh, and by the way, isn't this line right here tangent to my circle? Isn't this line here tangent to the circle? Yes, it is, because this line is barely skimming the surface. Remember we talked about points of tangency? Well, wait a minute. We said there was a special rule there for that. Well, we said that the radius is perpendicular. Excuse me. The radius, the circle, the edge of the circle is perpendicular to the point of tangency. So this radius right here is perpendicular with that tangent line. Same way if I had another radius that came out here, it would also be what? Perpendicular with this tangent line here. And the same way that this radius here would be perpendicular with this tangent line there. Okay? Now all of this came just from what? Just from my angle bisectors. Now let's see what happens with the perpendicular bisector. So let's make sure we understand that the incenter is the same distance from all of the edges, from all of the sides, all of the sides of the triangle. But now, let me make a perpendicular bisector here. Let's make some perpendicular bisectors. And we're going to label those in blue. Well, we know what happens with the perpendicular bisectors. Of a right triangle. They meet on the edge. But here is something that you may not know about the perpendicular bisectors. The perpendicular bisectors are equidistant from the vertices. So here's one vertex, here's another vertex, here's another vertex. If I measure this point here to all the vertices, they're all going to be the exact same distance. Let's take a look here. Let me take my ruler. Here. From this line right here to this vertices, it's 1, 2, 3 inches, 3.5 inches. It's about 3.5 inches to get to that vertex there. Well, if I measure from here to this vertex here, it's 1, 2, 3, and almost 3.5 inches as well. And if I want to measure from this vertex to this end here, well, let's take a look here. It's going to be 1, 2, 3, and almost 3.5 inches. So what do we know about, what can perpendicular bisectors tell us? Perpendicular bisectors come together at the circumcenter, and we know that the circumcenter is equidistant from the 3 vertices. They're equidistant from the 3 vertices. Let's take a look here. Here's another triangle where we have our circumcenter. These are all perpendicular bisectors, right? Let's measure from here to all the vertices, and let's see if that's true. Let's see if it's true. Well, from here, it's going to give me 1, 2 inches, 2.25 inches. Let's look at the next one. From the circumcenter to this vertices, 1, 2.25 inches. And from here, if we look again, guess what? 1, 2.25 inches. So this circumcenter is the same distance from all of the vertices. Well, that's helpful then. If I have a triangle, and let's say this is the circumcenter here, and I ask you, well, the lines may not look the same, but these lines are, these lines meet at the circumcenter. Can you please tell me how long these segments are? Well, then you would know that all segments are what? That they are all congruent. So we know that the circumcenter, is equidistant from all the vertices. But how do we get the circumcenter? The circumcenter is made by what? By the perpendicular bisectors. By the perpendicular bisectors. So guys, we've talked about points of tangency. We've talked about the incenter of a triangle. We've talked about what angle bisectors can tell us about a triangle, and what can perpendicular bisectors tell us about a triangle. So let's see if we can work on an assignment together. Today,